Let's move on to 5.2 heating effect of electric current. So in this part of the video, we'll talk about resistance. And actually, you have learned about resistance in year 10. So I would try to revise it with you, but I will expect you to have some basic knowledge about the resistance. Here is a very good paragraph showing and talking about the basic idea of energy and also resistance. So let's take a look here. So it said, as you learn about electric field in 5.1, so in a circuit that you learn in year 10, the one that gives out electric field probably is the cell. And then maybe there's a resistor here. And then that is the simplest circuit, right? So the electric field could be set up by the cell here. And so the electron, if you remember, this side is negative, this side is positive, then electron actually go to along this way, so in the clockwise direction in my diagram, because they push from the negative terminal. So what happens is when they move through, or when the cell, I should say, the cell is there and the circuit is all completed, there would be the electric field set up, and that would accelerate the free electron along the whole wire. So along this whole wire, all the electron will be accelerated and gain energy, and they will gain, of course, kinetic energy in that case. However, when we say there is a resistor out here, then those energy will be taken away and it would dissipate on to this resistor. And what happened in the microscopic view, according to like what you could also read here, is that they will have something called inelastic collision. If you remember in momentum chapter 2, we learned about inelastic collision. That means what happened to energy? That means the energy would be lost to the other object. Okay, so for the electron itself, they don't retain all the energy. If you retain all the energy, that is called elastic collision, right? 100% of the energy still remain in the system. But for inelastic, like this case, some electron energy, which is kinetic energy or macroscopically electrical energy, will transfer to the resistor. Because what happened in microscopic is along this whole resistor is actually, actually any wire will be like that too. There will be some atom. Actually, they should form very regularly, but I'm just trying to draw like in this random diagram. So when the electron try to go through them, there must be a chance that the electron will collide with the atom, and as if you try to strike a ball through these obstacles, the ball may hit on the obstacle and transfer the energy to this so-called obstacle, which is the atom of the wire itself. And so that's why they will lose energy. And in terms of energy, and this is how, when we say the voltage, if you recall what you learned in year 10, would drop when you pass through the whole resistor. And where does the energy go? The energy will simply go to, of course, the resistor or the wire itself, and that's why for light bulb they would be emitting light. For resistor, they will simply be heating up instead. So that's why here there's a very important word, macroscopically, that would increase the temperature of the wire. Okay, so here is some more detailed idea you need to understand in IB physics. Let's take a look of a more quantitative way. Here there's a definition, and let's take a look. Everyone should know this is the equation you learned in year 10. In year 10, more often we write V equals IR, because it's just when I was teaching, or most of the teachers when they are teaching, maybe it's easier to write so that you don't have to worry about the fraction, because simply like some students are just very scared with the fraction. But in fact, this is not a very good way to express. The better way to express is like this way. Okay, you may say, hey, what's the difference? It's just changing the term. This is better in physics because we are defining R. Okay, we are defining resistance using V and I. And what about V and I then? If you recall what we learned in the previous chapter, chapter 5.1, I'm talking about, we talked about V also. V was work done over charge Q, right? How many work done per charge? So this is a definition, remember. Okay, basic definition of voltage. And as in for current, do you remember what it is? It is change of charge over change of time, or how much charge passed by in each unit of time. And these two will be the definition, and this is a definition for R. So if you are saying, hey, so what about V? Can I define V as I times R? You cannot, because this is not simply the definition of V. This is just a relationship you can derive between these three. Okay, and same for I. You can't say I is, well, of course you can, but you can't say I is defined by V over R. Alright, you can't say defined, okay, but you can say they have such relationship. Okay, so be very careful with what is being defined, what is being derived. Okay, so here is the definition for resistance, and let's take a look at the wording. Is that if you have resistance R for a certain conductor, actually insulator as well, is defined as the potential difference V, which is all you can see at the top of the fraction, across it, because we know potential difference has 2 points, right? V has 2 points, divided by the current passing through it. So basically they just repeat what you can see here. However, I would like to add one thing, and you may want to add it in your textbook as well, or on your notes as well, is that this is only true when the temperature is constant. So what I'm saying is, when we talk about Ohm's law, okay, Ohm's law is a little bit similar to one law that you learn in physics, and that is Hooke's law. Hooke's law. Okay, do you remember what Hooke's law is? Hooke's law, okay, let me get some space, is referring to spring, usually the elasticity, and the graph we usually draw is what? Is F against the extension, right? So usually in year 9 we learn about that at the beginning. It's proportional, it's a straight line, and then somehow it will curve, and then we talk about this is the limit of proportionality, this is the limit of elasticity, right? And when we say it is, well, this spring or this string is following Hooke's law, we only say that it is following Hooke's law in this section only, because this is a straight line. Okay, I didn't draw very straight, but assuming this is a straight line, okay, this part will follow Hooke's law. Okay, but for here it does not follow Hooke's law, okay, because it's curved, and Hooke's law is simply F equal to Kx. K is remain as a constant. That means F and X are directly proportional. Similar to Ohm's law here, we are saying that V and I are directly proportional. So if something that is not having directly proportional, like the relationship between V and I is curved, then we don't say this is Ohm following Ohm's law, or we call it non-ohmic. Okay, I'll show you some example very soon. So this is an idea of why we are so emphasizing it needs to be a straight line. Okay, and that's why we emphasize why temperature has been constant, since you know when temperature change, the resistance will also change as well. Okay, so in terms of unit, it should be quite simple. Is V is volt, I is ampere, and for resistance the unit is ohm. Okay, or the symbol here, this is a symbol omega in Greek letter. For pronunciation here, we'll simply call it ohm for resistance. Okay, so yeah, that's pretty much for this page. So before you flip to this next page, please don't I'm going to show you the note, so you may want to take it out. And right now I want to give you a challenge here. Okay, give you a challenge. So in year 10 you learn about different electrical components, so including let me write maybe here, okay, including a fixed resistor, including maybe thermistor, including dial, including the filament or normal wire, or like the normal wire, normal metal wire. So there are 4 choices here: 1, 2, 3, or 4. 4 as in like the normal wire. And here I got 4 graphs here, which shows their property or the relationship of I and V. I want you to pause the video now and try to match which one is which one. Okay, you should know what these things are: fixed resistor, normal wired, thermistor, and dial. Okay, pause the video now and we'll check the answer. Okay, so let's take a look here. So what we have is, first of all, I think part A is very simple. This is a straight line, so this is the easiest question you can do. You can see that the resistance is fixed, it's the same slope anytime. Actually, if you really want to study about the resistance, then you may recall the equation V over I just now we just mentioned. So you may see that, oh, the slope is the same, so R is the same. Yeah, you may say so, but it's not actually correct to say that. I'll explain to you why. Okay, so this is sorry, not resistor, resistor. Okay, fixed resistor. So the next one, part B, you can see that the resistance apparent is not the same, and you may, if you try to look at the slope, you may say that, hey, the resistance it was quite steep, and later on it will get less steep, so resistance decrease, right? But I would say be careful with that. This is not the correct way of doing it. Okay, I say again, this is wrong. Okay, so the actual way to see this resistance, let me zoom in a bit more, should be looking at a certain point, and then you try to draw a line from origin, and then try to evaluate its slope. Same for this one. Instead of looking at the instantaneous, the tangent slope, what you have to do is look at the point particularly you want to find. Let's say this is like 0.5 V, right? And I don't know what this is, but anyway, then you can look at the slope here. Okay, so this slope represents the resistance at this point. Okay, instead of this one. Okay, so the result you find may be similar, but then when you try to do some question in the future, be careful with that, because simply just many people thought the instantaneous slope is the answer, is the resistance. Give me 1 minute and I'll explain to you why. Why is that case? Why not looking at the instantaneous slope? If you look at the definition just now we mentioned, it is V over I. Okay, then you may say, hey, what's so special? It's V over I. Be careful. It is not dV over di. Okay, that if you don't understand differentiation, let me explain. This is not delta V over delta I. Okay, not this one. Well, you may say it's delta V, but it's not delta I in that case. Alright, so the difference between this and this is, we are, for this one, is really looking at the instantaneous slope. Alright, example would be when we talk about mechanics, we talk about VT graph, and then we say, oh, maybe like something like this. This is a VT graph, and then when we say, hey, the acceleration or the slope at this point is 0, and therefore A is 0. This is correct because A is defined as dV over dt, or if you don't like that, delta V over delta T. Okay, and therefore this is true. But the case when we have the circuit here, since we defined resistance as simply V over I, then you cannot use the instantaneous slope. So this is something you may want to bear in mind. Okay, so back to the question here. What we can find is when I is low or V is low, then this is a slope, which means R is rather steep, so higher, and then later on is lower. So think about that. What kind of device would be like this? And that would be lower resistance. Okay, so that should be a thermistor, right? Because when you draw higher temperature, when I increase, temperature should increase, and somehow you have lower resistance. Oh wait, no, I make a mistake here. Okay, be careful. What a mistake. This is I, this is V, so it should be opposite. So since the slope, okay, this is very tricky. V over I, right? V over I. So in fact, this slope is more like 1 over R. Okay, so for simplicity, I should say, since the slope is steeper, so actually resistance decrease, and then here resistance actually increase because the slope is less. Slope, again, in this graph is 1 over R. So if 1 over R is less, that means R is increased. Okay, so this is actually a normal wire. Okay, a normal wire which it will increase the resistance when temperature increase. Okay, so this is something that you should recall and what you learned in year 10. For part C is actually quite easy to recognize, because you can see that when current is negative, there's nothing. Okay, or I should say that I shouldn't say current. I should say voltage. Voltage is negative. There's no current, and only when voltage is beyond 2 positive, then you can have some current. And this is a property of the dial. Alright, if you don't remember what dial is the symbol looks like this, and it only allows one direction of current to flow through. So for example, this one, it only allows current to flow from left to the right. Alright, so left to right is okay. However, if you try to flow from the right to the left, you can see this symbol is more like a wall. It blocks you off. So no matter how much voltage you add, that means like here, there's no current at all. Because that is simply just a property. I can't explain too much right now using simple words, but if you're interested, you can try to search how the structure of the dial is. It's using something called the semiconductor. And so basically the behavior is strangely or interestingly, when you try to apply current in different directions, they will have different resistance. So for this one, the reason why they have almost no current is because the resistance will become enormously large. So that's why there's no current. Again, just like building a wall here. Alright, there's no currents to flow through. Okay, while for the opposite direction is rather easy. So this is how the dial works. We'll talk about more about dial in the future. For the last one, since you only have 4 choices, so this one must be thermistor. But let's also talk about why it is thermistor. So I don't know why actually like this part of the graph looks like this. Maybe this is really the basic property, like what happened to thermistor. But we would mainly look at this portion. Okay, this portion. So what this portion show you, this is by the way, there's one tricky thing on the graph. This is really V against I. So the slope here, or the slope you draw, will really represent you the resistance. So as I said, here, this is what you have initially. And then this is the slope for later on. So you can see the slope is decreasing. And that means resistance is decreasing. So one less. The slope is less, the slope is less, the slope is less. So that means resistance is decreasing when you are having more current. As again, when you have more current, that means temperature increase, and from what we find from the graph, R decrease. So this relationship, temperature increase, resistance decrease, would match with the idea of thermistor. Okay, so this is something that 4 components that you learn in year 10, and this is their graph. Okay, it's a very interesting way to interpret on the graph.